Hello, math friends. This is AP Calculus Section 2.9. Imagine if we had some function f and we wanted to calculate an exact value for f of a. But what if we wanted to calculate values of the function near a, but not exactly at a? We could create a linear function, we'll call it L of x, which is the tangent line to the curve f at a. In fact, we've done this already this year. We can then use this linear approximation to calculate nearby values on the curve. So this section is about writing equations of tangent lines to curves at specific points and then using those equations of the tangent line to approximate values for the curve. Recall that the slope of the tangent line is the derivative of the function at x equals a, which we can always find using our different quotient. F prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a. Then we can use our point, which is a f of a, and point slope form to write an equation for the tangent line that we seek. In general, we can use the tangent line at a f of a as an approximation to the curve y equals f of x whenever x is near the value a. And our equation for this tangent line is y equals our f of a plus f prime of a, which is our slope, times x minus a. This approximation is called the linear approximation or the tangent line approximation of f at a. The linear function whose graph is this tangent line is called the linearization of f at a. So in this section, we are talking about linear approximations, but what you need to understand is that a linear approximation is merely the same thing as a tangent line at a given point on a curve. Let's take a look at example 1. It says find the linearization L of x of the function f of x equals x to the fourth plus 3x squared at a equals negative 1. Okay? And I apologize, this is not supposed to be here. I changed my function, so we're just going to cross that out. That's not on your paper, just on mine. So taking a look at our function, the first thing that we need is we need a slope, right? So our f prime of a is going to be equal to the limit as x approaches a of f of x minus f of a divided by x minus a. There's our difference quotient for finding our slope. So in order to use this difference quotient, it would be nice if we knew what the value of f of a was. They told us that a is negative 1, so if a is negative 1, f of negative 1 is going to be equal to negative 1 to the fourth power plus 3 times negative 1 squared, which when we do the math, negative 1 to the fourth is 1, negative 1 squared is 1, so 1 plus 3 is 4. So we find out that the ordered pair, negative 1, 4, is our a, comma, f of a ordered pair on our curve. All right, so let's go ahead and do our difference quotient here and find our slope. So f prime of negative 1 is going to be equal to the limit as x approaches negative 1 of our function, which is x to the fourth plus 3x squared minus f of a, which we just found f of a is 4, divided by x minus a, which is negative 1. Well, minus a negative, chop chop, that becomes plus. Now, we can't just do our substitution of negative 1 because negative 1 plus 1 in the denominator is going to make 0. So that tells me that I must be able to factor my numerator. And although it is x to the fourth x squared constant, this is still just regular trinomial factoring right here. So we are just looking for a pair of numbers that multiplies to make negative 4 and adds to make positive 3. And that pair of numbers is going to be positive 4 and negative 1. Now hang with me for a second. On the bottom, we have x plus 1, so that's what we're trying to get rid of. But keep in mind, when we factor our numerator, because we had a 4th degree trinomial, our two factors are going to be x squared plus 4 and x squared minus 1. Now, one of those is a difference of squares and can be factored further, but the only one that's a difference is the x squared minus 1. The x squared plus 4 cannot be factored further. So f prime of negative 1 will be equal to the limit as x approaches negative 1 of x squared plus 4, and then x squared minus 1 factors into x plus 1 times x minus 1, and our denominator has the x plus 1. So now we can go ahead and we can cross out those families of x plus 1. That was our problem. And then we can actually evaluate the limit. So f prime of negative 1 is going to be what we get when we plug negative 1 in for x. So we're going to get negative 1 squared plus 4, that quantity times negative 1 minus 1. Which, when we do the math, negative 1 squared is 1 plus 4 is 5. So that gives me 5 times. Negative 1 minus 1 is negative 2. 5 times negative 2 is negative 10. So that tells me that f of negative 1 is negative 10, which is going to be the slope of my linear approximation. So now the next step is going to be, we are going to think point slope form here. We know our point slope form is y minus y1 equals m parentheses x minus x1. And if we were to solve that for y, we would just be bringing that y1, we'd be adding it to the other side. So y would be equal to y1 plus m times x minus x1. But when we think in terms of the tangent line at a point on a curve, our linear approximation, our L of x, is going to be equal to the y value of our ordered pair, which in this case is our f of a, which is, we know is going to be 4, plus our slope, which is our f prime of negative 1, times our x minus our a value. So here is the point slope form version of our linear approximation. Now we just have to plug our information in. So L of x is going to be equal to f of a, which is 4, plus our slope, which is negative 10, times x minus our a value, which is negative 1. And again, minus a negative, chop chop. So we can simplify. L of x is equal to 4 plus negative 10x minus 10. And then finally, combining like terms, our linear approximation is going to be negative 10x minus 6. And again, I just want to reiterate that this was the exact same process as finding the tangent line to the curve at a given point, except in this section we are calling it a linear approximation to our curve, or to f at a. Example 2 says for the function f of x equals the square root of 1 minus x, part A, find the linear approximation of the function at a equals 0. Part B, use that approximation to estimate the values of the function for x equals 0.1, 0.01, and 0.001. Part C, use your calculator to determine the actual values, then determine if your values are underestimates or overestimates. And then finally, Part D, graph the function on the tangent line and make sure the graph supports your solution for Part C. All right, so let's take this one step at a time. Part A, we need to do the exact same thing we did in example 1, which is to find the linear approximation of the function at a equals 0, or in other words, find the tangent line to the curve at 0. All right, so step 1, we need to find our slope. We know that our a value is 0, and our f of a is going to be equal to f of 0, which is the square root of 1 minus 0, which is 1. Square root of 1 is 1. So our point is the 0.01. All right, let's find our slope. F prime of 0 is going to be equal to, I need to do my difference quotient, the limit as x approaches 0 of f of x, which is the square root of 1 minus x, minus f of a, so minus 1, divided by x minus a, so divided by x minus 0. All right, now we look at this, and hopefully the first thing that comes to mind when you see this difference quotient is perhaps I should try rationalizing the numerator. And that's exactly what we need to do, because we know that we're going to have to get rid of that x in the denominator because we're not allowed to divide by 0. So I am going to try RTN. I'm going to try rationalizing my numerator, which means I'm going to multiply top and bottom by the conjugate of the numerator. So if I have the square root of 1 minus x minus 1, I am going to multiply top and bottom by the square root of 1 minus x plus 1. And then when I do that, in my next step, I will have the limit as x approaches 0 of, in my numerator, when I FOIL conjugates, I only have to do first and last, inner and outer cancel. So square root of 1 minus x times square root of 1 minus x gives me 1 minus x. And negative 1 times positive 1 gives me negative 1. In the bottom, x minus 0 is just x. And again, I don't want to distribute that. I want to leave it because I am hoping to cancel that x. So I'm going to leave it separate. All right, now in my numerator, I have some like terms. My positive 1 and my negative 1 cancel out. So now I have the limit as x approaches 0 of negative x over x times the square root of 1 minus x plus 1. And now you can see, just as I had hoped, this x and this x cancel. So now I have the limit as x approaches 0 of what's left in my numerator is just a negative 1 divided by 1 minus x, the square root of that, plus 1. So now I can go ahead and I can evaluate this, which is going to be negative 1 divided by the square root of 1 minus 0 plus 1, which is negative 1 over 1 plus 1, which gives me negative 1 over 2. So that tells me that the slope of this linearization, or this tangent line, is going to be negative 1/2. So now I'm going to go ahead and I'm going to finish up part A, which is just going to be to write that linear approximation. So again, here's my equation for the linear approximation. It's L of x is equal to f of a plus f prime of a times x minus a. So for this particular function, my f of a is 1, my f prime of a is negative 1/2, and my a value is 0. And when I simplify this, I get L of x is equal to negative 1/2 x plus 1. So here is the answer to part A. My linear approximation is the line negative 1/2 x plus 1. Part B is simply asking us to use our linear approximation to estimate the values of the function for x is equal to 0.1, 0.01, and 0.001. Oops. So I'm just going to make a little table of x values and of L of x values, and I'm going to need my calculator in a second here. But the x values are 0.1, 0.01, 0.001. So I'm just going to go ahead and I am going to plug those into my linear approximation, which again is just negative 1/2 times my x value plus 1 And for those values, when x is 0.1, I get 0.95. When x is 0.01, I get 0.995. And when x is 0.001, I get 0.9995. Part C asks us to use our calculator to determine the actual values of the function. So the easiest way to do part C would be to use the table function in the calculator by plugging f of x into y1. So I am going to open my graphing calculator and I'm going to enter my function into y1, and then I'm going to go to the table and plug my same 3x values in and see what the values of the function actually are at those 3 locations. My function is the square root, so remember that second level function above the x squared, of 1 minus x, all under the square root. And so now I'm going to go to table, and again you can just type right on top. So I get 0.1, 0.01, and 0.001. And so I can go ahead and I can record those 3 values in my table. For 0.1, I got 0.9487. For 0.01, I got 0.9950. And for 0.001, I got 0.9995. All right. So then the second part of part C is determine if your values are underestimates or overestimates. So if we go back here to this problem, what part C is really asking us right here is, does our linear approximation give us values that are bigger or smaller than the actual values of the function? So let's write that down. Does L of x give values bigger or smaller than f of x? So that's the question that we're trying to answer here. That would tell us if our values are underestimates or overestimates. So when we look, we can see that the values that we get for L of x are larger, right? These are larger. These are smaller. So that tells us that our tangent line, our values for L of x are overestimates. So what does that mean in terms of our graph and our linear approximation? So that means that L of x must lie above the curve f of x. Okay, if our values are overestimates, our tangent line is above our curve. If you think about that, that should make sense. If our values were underestimates, we would expect our tangent line to lie below our curve. So finally, part D asks us to graph the function and the tangent line and make sure that the graph supports our solution from part C. So basically, make sure that once we graph our function and our tangent line does indeed lie above the curve. So for the last part here, I am going to graph f of x and L of x, and we'll see what we have. Let's begin with our function f of x. Recall that f of x was the square root of 1 minus x. Well, we know what the square root of x looks like. The square root of x is, it starts at 0, 0, and it's kind of a sideways half parabola, right? Well, this is just a series of transformations on that function. So if we were to, first of all, factor out a -1, then we would have -1 times x minus 1 under our radical. So this x minus 1 is a shift 1 to the right, and this -1 underneath the radical is a reflection over my y-axis. So you could certainly grab your graphing calculator to graph this, but the point I'm trying to make is that this is just a transformation of a parent function that we should know. So technically we shouldn't really even need our calculator. We should be able to do it without. So I know that my graph is going to start here at 1, 0 because it's shifted 1 to the right. And then instead of going up and to the right, it's going to go up and to the left, but it's going to hold the same shape as the parent function. So I'm going to have a point that is 1 to the left and 1 up, and then I'm going to have a point from the start that is 4 to the left and 2 up. And my curve is going to look like that. So now my L of x, my linear approximation, I know that's the point -1/2 x plus 1, which is just a slope-intercept equation. It has a y-intercept at +1, and then it has a slope of -1/2. So I'm going to go down 1, right 2, down 1, right 2. I could also go up 1 from the y-intercept, left 2, up 1, left 2. So here is my L of x. And as you can clearly see, L of x is tangent to the curve at the point 0, 1. That was my A f of A. And L of x does indeed lie above the curve, which proves that the work that I did during the rest of the problem is correct. Example 3 gives us a table, and the table shows the population of Nepal in millions of people as of June 30th of that given year. They ask us to use a linear approximation to estimate the population at mid-year 1989, and then use another linear approximation to predict the population in 2010. Well, first of all, if we think about population growth, normally the shape of population growth is exponential. So it would not make sense for us to use the same linear approximation for the year 1989 as we would use in the year 2010, because the slope of the curve would be drastically different at those 2 points in time. So we will need to find 2 different linear approximations to answer this question. So I'm going to call it part A and part B. So for part A, I will say that we want to find a linear approximation for mid-year 1989. All right, so all we have to work with is a table of points. That's it, that's all we have. So that is the best information we have to work with. Well, 1989, mid-year 1989, lives between these 2 data points, between 1985 and 1990. So it makes sense that these are the 2 data points that we use to find our linear approximation. Those are the 2 closest ordered pairs to the value that we are trying to approximate. So my f prime of A is simply going to be the slope between those 2 ordered pairs. So 19.33 minus 17.04 divided by 1990 minus 1985. You grab your calculator, you do the math, you should get a slope of 0.458. Now that I have my slope, the next thing that I'm going to do is write my linear approximation. So the point that I'm going to choose is going to be the point that is closer to 1989, which in this case is 1990. So that's the point that I'm going to use for my A f of A. So my linear approximation is going to be equal to the y value of my point, which is 19.33, plus my slope, 0.458, times x minus the x value of my point, which is 1990. And then when I do the math here, I get L of x is equal to 19.33 plus 0.458x minus 911.42. And then finally combining like terms, I get L of x is 0.458x minus 892.09. So now to answer the question, we want to know the linear approximation for mid-year 1989. Well, mid-year 1989 is like 1989 and a half, right? So I am going to find L of 1989.5 because that would be mid-year 1989. So I'm just going to plug that in for x. So 0.458 times 1989.5 minus 892.09, which gives me an answer of L of 1989.5 is equal to 19.101, and this is million people. Okay, so there is our linear approximation for mid-year 1989 based on this table. All right, now our part B, they want us to just repeat this process, but now they want us to do it for the year 2010. Well, this is an interesting question to ask us to do because if we look at our data set, 2010 is out here, right? It is beyond the last bit of information that we have. But again, we can only do as good as the data that we are given. So once again, I have to choose two ordered pairs in my table to find my slope and to write my linear approximation. So the two closest ordered pairs that I have to work with are going to be these two ordered pairs. So my part B is going to be my L of x for the year 2010. And I'm going to start again by finding my slope, or my f prime of a, which is going to be the slope between those two ordered pairs. So it's going to be 27.68 minus 24.70 divided by 2005 minus 2000. Grab your calculator, do the math. You should get a slope of 0.596. Now I am going to write my linear approximation. And again, I have to choose an ordered pair here, right? So the ordered pair that I'm going to choose is going to be the one that is closest to 2010, which is going to be this one. So my L of x is going to be equal to 27.68, that's the y value of my point, plus my slope, 0.596, times x minus the x value of my point, which is 2005. Now we do some algebra. 27.68 plus 0.596x minus 1,194.98. And then we combine our like terms and we get a linear approximation of 0.596x minus 1167.30. And then if I want to use this linear approximation to estimate the population in 2010, I'm just going to plug in 2010 for x. So 0.596 times 2010 minus 1167.30 gives me a linear approximation in 2010 of 30.66 million people. All right, now this question says that we were supposed to do these two linear approximations. My question for you, after doing the math and thinking about what you know about linear approximations, is which one of these is a better linear approximation for the question that we are trying to answer? And hopefully you understand that part A is a much better approximation than part B, because 1990, that ordered pair, is very close to 1989. So using that as your point for your point slope form makes good sense and gives us a value that we can feel is pretty confidently a correct value for our linear approximation for mid-year 1989. However, for 2010, we are extrapolating pretty far out here. We don't have any data beyond 2005, so we're making a huge assumption that a linear approximation for 2005 is going to be close enough to what it would look like in 2010, which in my opinion is not going to be very close to the accurate value.